left off with electrons and the quantum theory. Now let's talk about the postulates we've already spoken about. I've already told you about, and I'm going to stick with this, two simple postulates. Electrons can only exist in certain energy states, but they can change those energy states. They can change those energy states by getting energy energy in the form of, well, three different ways, as you're going to see today. We've already given you one of them. I gave energy to these two solutions. Okay, take a look. Turn that light off for me for a second. Remember this from yesterday. I took little blue light, black light, I should say, and this one, the tonic water, glows blue. I'm exciting the electrons in the quinine that's in there. All right, and if you look at that, this guy's glowing blue. Why? Because his electrons are getting excited. They're jumping up to a higher energy level. They're quantum leaping up to there, I should say. And when they can't, like anything else, I throw a ball in the air, it falls back down. When they fall back down, they give off energy. And then we see that energy in this case as a blue light. All right. Now, that's not the only way I can excite electrons. But let's talk about what happens to those and how they get excited. Okay. You have your atom, and he has energy levels. This is very simplistic. This is not really what it looks like. It's not rings at all. But we represent the energy by basically how far they are from the nucleus. This is the first energy level, second, third, and so on. Now, when I give that guy energy, whether it's by ultraviolet light or some other way, those electrons jump up to a higher energy level. They don't go to every spot in between. They're not allowed to be there. They can't exist there. They're here, and then they're here. And then they fall back down. And when they fall back down, they give off packets of energy. Because for the same reason, they can't fall through all of the parts. They can only give off a big packet of energy. I have a little animation to try to illustrate that for you, I found. Okay, if you look at this animation, here's your electron happily living there. He gets bumped by something else, some form of energy. Maybe it's another electron. Notice he doesn't go through every spot in there. He just appears out here. And then he falls back down. And sometimes that fall back down does happen in stages. He might drop to one energy level, like this guy does. He drops down to here. And he gives off that little lightning bolt is some photon of energy is given off when he returns to his ground state, his lowest energy state. Okay, that's what it's called. That's where he wants to be. That's where he's happy. He gets excited by this energy, and he falls back down and gives off energy. Okay, but again, it happens in bunches. That's a quantum leap. And then he falls back, quantum leaps back. All right? And that's why when this happens, you actually get specific colors that you'll see. It doesn't give off all the colors of the rainbow. It doesn't give off every color of the spectrum. He gives off very specific colors because electrons jumped a very specific amount of energy. Okay? And we can actually test this a couple of different ways. We've already seen one where I use ultraviolet light. Now we're going to talk about two other ways. Hit that backlight on so you can take the notes better. Flame tests and spectrum tubes. That's what the lab's on. We're going to start the lab today. You're going to finish it tomorrow. The bulk of the lab will be done tomorrow, where you have to do the flame tests. The spectrum tubes, I'm going to talk about today. Don't let anybody. All right, so I'm going to illustrate these for you because tomorrow I'm not going to have the time. You guys only have a single period. And I want to show you how to do these today, how to do the flame tests today. So I'm going to do that in a second. But just copy this down first. All flame tests and spectrum tubes are ways to excite electrons. I mean, how do you excite an electron besides showing it a picture of a naked electron? That might excite it. I guess it depends. You can excite electrons by giving them energy. And you give them energy in a number of ways. One of the ways we're going to do it, I'm going to illustrate for you right now after you copy that. We're just going to heat them up. We're going to put them in a flame. Put them in a Bunsen burner flame. That's what you're going to do tomorrow. All right, while the light's still on, before I turn it off, let me show you something. This is the wire you're going to use, if you can see this. Okay? Now that wire has a little loop in it. See the loop? Okay? Now that loop is where you're going to dip into a solution, an unknown in some cases, and other ones that you do know, and you're going to catch a little of the solution in that loop, and then you're going to put it into the flame and get it excited, get the electrons excited. All right, when that happens, they jump to higher energy levels, like you just saw a second ago. When they fall back down, they give off different colors. Let me show you that right now. First, when you get this wire, first thing you have to do, first of all, I don't want you touching it. You shouldn't use your hands on it because your hands have lots of stuff on them, sodium from sweat. Okay, so you want to clean. It's probably not very clean, so you're going to want to clean it. Get your burner out. We're going to have to clean it using the burner and some very strong acid. So get your burner out, and you light it, like you always would. Let me make this dark here and turn that light off for a minute. Okay, get my burner going here. There he is. Now, I want to dip this in the acid first, the wire, just the wire. I don't want the glass to get wet. And then I'll put that into the flame. And I want to put it about 2/3 of the way up in the flame. And you notice there's not a whole lot of color being given off here. Not a whole lot. But it is glowing what? What color is it glowing?
Orange.
Orange. Okay. But there's not a whole lot of color above the flame, as you'll see. You can clean this off a couple of times. Dip it in the acid. And that's very strong acid, by the way, 6 molar acid. And then put it into the flame. You'll see some color. Sometimes they're hard to burn everything off that you've used before. But this is pretty clean. I don't see a whole lot of stuff above it. This wire, by the way, is not melting in the flame. It's made of platinum, and it cleans off very well. It's very good for this use. So it's a platinum wire. Yeah, the same kind of platinum. It's very expensive. This little wire here, when I buy it, I usually buy a wire that actually can make 3 or 4 of these, about that long. Maybe I could cut them and make 3 or 4 of them. And it's usually like, I don't know, $60 or so for this very, very thin platinum wire. I haven't bought it in a while because these lasted me quite a while too. Now, you're going to get your solution that needs to be tested. They'll be in bottles back there at the tables. You're going to see tomorrow about 7 or 8 different bottles, each of them labeled with what's on it. Okay? They'll be in bottles like this. All right? And each one of those bottles is going to say something on it. So say I wanted you to test this guy, who happens to be boric acid, and I'm going to test the boron atom. I want to excite his electron. So I'll dip this. Turn the light on for a second. I want to show you something. I want to dip this, just the tip of it, into the solution. So I want to keep my eyes open and make sure I just get the tip of that in the solution. Okay, light off. Now I'll put it in here, and let's watch what the color does now. See it? Did you see that little flash there? Maybe you didn't. So we'll dip it again. It's no biggie. You can leave it off. I can see now. I just wanted to show everybody else. What color do you see? You see that green flash? Okay. Now, it didn't last very long. It happened kind of in the beginning there, a little flash of green. You would write that down as your observation. Now, I want to test somebody else and see what color he gives off when his electrons get excited. Can I just dip it into the next solution? Yeah, I better clean it first, because if I just dip it into the next solution, I'm going to contaminate that solution, and I'm going to get 2 different colors anyway. I'm not going to be able to tell which was which. So I'll dip it in my acid again, into the flame, try to get rid of any color that's on there. Notice I'm holding it about 2/3 of the way up the flame. Acid, flame. If I hold it way down here, notice it won't get as hot. It doesn't really glow orange. I want it to be glowing orange like that. See it? All right. All right, let's assume that's cleaned off enough. And let's test another guy. Okay, you won't be testing that one over there, boron. All right, you're going to be testing this guy, though. This guy will be one you'll see. I just want to dip the tip of it in there. The reason I want to only dip the tip is I can't dip that whole wire into the flame. Oh, see that color? See that? That's pretty obvious, right? What color do you see there? Notice how if this one's burning like more towards the end. What color are you seeing? Like, fuchsia. Yeah, like a very, very deep red. Fuchsia would be a good description of that color. And if I don't see that, I can dip it again. That one's pretty obvious, and do it as many times as I need to. However, you don't really need to see that one again. Before I go on to the next one, I want to put this in the acid and clean it off. Now, I want to make sure I don't get the solutions too far in on this wire, because then I can't clean it off. Because I don't want that glass going into the flame, do I? What's going to happen if I put that glass in the flame? It gets hot, it gets cold, it gets hot, it gets cold. What's it going to do? It's going to crack. All right. I also can't clean it off, because if I can't put it in the flame and that stuff's on there, it's going to drip down. So here's one of the big problems I'll get. People who aren't paying attention just go and dip it in the butt, put the whole thing in there, and it's like dripping down with the solution on it. How am I supposed to clean that off? Well, the only way to clean it off would be to dip the whole thing in acid and the whole thing into the flame, but that's a problem. I don't want you to do that. It's going to crack it. All right, what am I doing here? I'm exciting the electrons. They're jumping up to higher energy levels. They're falling back down and giving off colors. And notice everybody has a different color. Now, the problem is there are about 100 and some elements in the periodic table. Some of those colors are going to be similar, aren't they? All right, so I got to have a better way than just flame test. I got something else I can do and something else I can use, even with a flame test. And I'm going to talk about that right now. Okay, turn that light back on. Let me shut this off. Check this guy out. Well, before I get to him, let's do something else. All right. In everybody's case, in the case of all of these guys, whether it's the ultraviolet light, the flame test, or this, what I'm about to show you, the spectrum tubes, everybody's doing the same thing. His electrons are getting excited. They're moving up to a higher energy level. They fall back down. They give off energy in the form of specific packets of energy, in the form of sometimes visible light that we can see as a color. Guys, the reason this works, what's the difference between the colors? What makes red versus green versus yellow versus blue? The wavelength. So if this guy has different energy change, he has a different wavelength. Now, not all of them are given that wavelength off in the visible spectrum, but a lot of them do. And so I can see different colors these guys give off, and I can identify them. I can actually identify them. All right, let's now look at what we're going to do next. I want to get to that yet. I want to do this first. Do I have a black screen here? Yes, good. All right, let me show you how to use this guy. This is what you're going to use today. You're going to be back in a few minutes. Turn that light off again. And you are going to be, let's see which one this is, okay. You're going to be testing a whole bunch of these spectrum tubes. Okay? Light on for a second. These spectrum tubes are all pretty much the same. They've had the air sucked out of them. They're pretty much a vacuum, with the exception of a very small amount of some individual element from the periodic table. This guy has hydrogen. Hydrogen is in this one. A little bit. Mostly nothing's in here. Mostly it's a vacuum. If I break this, you'd hear a nice little pop, because if I had a lot of air in here and I tried to pass electricity through it, not much is going to happen, because air is a good insulator. It's not going to be able to jump across this space. So I have the air sucked out of it with the exception of a little bit of hydrogen. This guy has a little bit of argon. Let me show you what happens when I excite these guys' electrons, not with heat, but with electricity. Okay, turn the light off again. I put them in here. I pass a current through them, and you got to plug it in, or nothing happens. Let me plug this guy in. Try it again. There we go. What color is he glowing? Yeah, it's a nice color. It's pretty easy to see. See, it's a little bit better way than a flame test. Okay, it's a very consistent color. I could describe this color. It's a little bit better. There's something else I'm going to do in a second to make it even easier. All right, that was hydrogen. This is argon. Because if you're not here, you are gone. It's funny. Argon. Argon's element periodic table, right over there. Notice the color of this guy. Everything's fuchsia.
Purple.
Yeah, this one's more of a purple color. I wouldn't call that fuchsia at all. That's more of a purple, but a slightly different color, right, than the last one. Now, this last one I'm going to test here. It's a very familiar one.
Students taking the PSAT tomorrow. I would like you to bring with them a calculator and number 2 pencils. Members of the girls' tennis team will meet in the cafeteria at 3 o'clock.
What element is that?
Anyone who has not yet handed in their uniform must bring it with them to the meeting today.
What's that?
Members of the homecoming court and fall
She doesn't know. She's not going to answer.
to be in the cafeteria tomorrow morning.
You guys all know what's in this.
Verified photo. Senior football player.
Think of Times Square. What?
And at this time, all
Exactly.
please report to the auditorium. Thank you.
Neon, as in neon lights, right? Broadway, right? Yeah, that's what a neon light is. All a neon light is a glass tube with most of the air sucked out of it and a little bit of neon added to it. Because when neon gets excited, this is what he does. His electrons give off a very bright red color. And that's what we make neon signs out of. You might be saying, well, what about signs that aren't red? What are they made out of? Well, they're not made out of neon. They're probably made out of something else. Some other gas that's in there. Because you've just seen several other colors that you can see. Okay? This is a spectrum tube. We're exciting electrons again. A third way to excite electrons. But that's not enough. I still would have multiple colors that would be very similar. I can break that guy down. I could break down that color into the individual wavelengths that are being given off when this guy gets excited. And I'm going to show you how I can do that right now. Okay, turn that light back on. But first, I want you to copy this little bit of notes here. What you are going to see, what I'm about to describe, is what's called the atomic spectrum. It's what you will visualize when looking at a flame test or a spectrum tube through what's called the spectroscope. When you look through a spectroscope, you will see what's called the atomic spectrum. They are characteristic wavelengths of light given off by the atoms when these electrons are returning to their ground state or their normal energy levels. Okay? First of all, let me tell you what it does. Okay? If I just have a light bulb that I plug in here, okay? Let me plug this light bulb in. And I take a prism. And I look at that light through a prism. Maybe I should move this out of the way for a second until I show you what's happening here. Turn that light off again. Okay? If I look at the light of that light bulb through a prism, which you're going to do, don't look now, okay? Which you're going to do in a second, because that's what I just passed out to you, those spectroscopes, okay? The light, when it hits the prism, will actually break. The white light consists of all the wavelengths that you can see, all the colors of the rainbow, purple, Roy G. Biv, all of them, okay? When you hit a prism, the prism itself is going to, the different wavelengths are going to travel at different speeds through that prism. So it's going to break it up into its individual wavelengths. Okay? The purple and the red and the yellow are all going to exit at slightly different places from that prism. Water can act as a prism if the light hits it at the right angle. Okay? And then you see a what? A rainbow. You know, that's the light has to be traveling at the right angle, and then you'll see a rainbow. Okay, so if light hits this prism, it breaks it up. Now the thing is, white light will show you all the colors of the rainbow, and that's what I want you to see now. I'm going to turn on around the room. There are a bunch of light bulbs, and you now have in your hands a spectroscope. Let me show you how to use a spectroscope. Okay, you're going to have, turn the light on so you can see. You're going to have, I purposely put, it seems silly, but I put top on because there was no other thing on there. So you didn't know which way to hold it. This is the top. So with the top up, that's why it says top. This is the eyepiece, okay? All right, and I'm going to have you, you're going to look through this at a light bulb, which I have to turn on now, all right? Let me do this. An incandescent light bulb gives off all the colors of the rainbow. So you're seeing a rainbow when you look through that spectrum. Same thing you see here. Now, what you're going to do, I'm going to turn the lights on. Whoops. That was probably one that's going to be broken. I'm going to turn the lights on above your head. And I want you to use that same spectroscope and look up at those lights. Turn both lights on. Okay, look at that look at the thing up above you. Same way you were looking before with the top. Notice you've got the rainbow, but it's not exactly what it was before. It's not a continuous spectrum, is it? There are lighter areas and there are darker areas, aren't there? Right? Y'all see that? Y'all see the bright lights, bright lines? And the darker lines, right? That's because those fluorescent bulbs up there, those bulbs, they're the same thing as this guy right here. Only instead of having, obviously we don't want to be sitting here with a red light on. This isn't the red light district here, okay? We basically have a mixture of gases up there that will mimic sunlight for the most part. It's not exactly the same. We all know that. Girls know that especially. You go shopping in a department store, you try something on, it looks one color, then you take it home and it looks something else. Because at home, we don't usually use fluorescent lights, okay, for the most part. Or out in the sunlight, you look a little bit different, right? So that's got brighter and darker areas because it doesn't have all the wavelengths of light given off. This, of course, glowing with its orange color, or red, I guess this is a neon, right? This guy glowing with his red color is going to have even fewer. If I look at this, and you can't from where you are, but you're going to go back there in a minute and look at them back there. That's why I wanted to have more time. I'm going to send you back in small groups. When you look at it here, you know what you're going to see? You're going to see, turn that both lights off here. You're going to see, well, first we'll go back to the regular light bulb. You'll see all the colors of the rainbow, okay? A nice continuous spectrum. But when you look in a minute at a flame test or a spectra tube, and let me get this guy out of here so he's not in your way. When you look at that, you know what you're going to see? You are not going to see all the colors of the rainbow. That red is only consists of a certain wavelength that were given off when those electrons in strontium, in this case, fell back to their ground state. What you saw with your naked eye was red, but that red was actually made up of multiple colors. And you look through a spectroscope, and that's what you're going to see. You're going to see all these bright lines. This is called a spectrum, atomic spectrum. And you're going to see these lines. They correspond to those electrons returning and giving off, turning to the ground state and giving off energy and photons. And notice, what we see is a combination of these colors. So hydrogen might have looked purple to us a little bit, or fuchsia, if that's what you saw. But the thing is, this is the final statement about this. Listen up. This is as absolutely unique as a fingerprint. It's as unique as a fingerprint. No two atoms in the periodic table have the exact same spectrum. So I can identify these things. And this is exactly what we have equipment now that can do. That you can identify unknowns in seconds. Right? Instead of having to go through a whole bunch of chemical tests, you know exactly what was in this compound, all right, just by running it through a spectral analysis. You can figure out what was in there. Because each element has its own spectrum. I can tell you exactly how much of it, the percentage of it, too. And then you just put two and two together, and you've got the compound. Some unknown, you can figure it out. It's used in forensic chemistry all the time. It's used in a lot of things, all right? Because no two atomic spectrum are alike. They're like fingerprints, all right? Now, you're going to go back. And right now, I'm almost done.